Welcome to Robots in Depth. Today I'm honored to have Gregory Dudek from McGill University. And we're going to talk about field robotics, I understand, right?
That'd be great, yeah.
Why did you go into robotics?
Also, I started out as a PhD student doing computer vision. And I think if you're doing vision, it probably becomes apparent relatively readily that one of the great applications of vision is in the context of robotics. There's both a need and a potential for applications, and so I just drifted into robotics as a result of that.
What kind of environments are your robots usually developed for?
Right. So in my own research lab, we have some indoor, more conventional kinds of robotics, and we also do field robotics. I think field robotics has been the larger part of my lab for probably on the order of a decade. For the first decade of my career, I probably focused more on kind of indoor work or theoretical work, actually, a lot of algorithmic proofs of complexity. How hard is it for a robot to localize itself in an environment, given, trying to find worst case bounds on that kind of thing? And in the last decade, more and more into field robotics. The reason is, well, there's a number of prongs, a number of justifications for that. One is there's a huge need everywhere in field robotics. Like there's resources, natural resources that have to be monitored in terms of trying to maintain them, as well as perhaps trying to exploit them. In my own case, I have been going to the island of Barbados for many years, where McGill has a research station and where we run workshops on diverse issues in computer science. And I came into contact with biologists who study the coral reef. And the coral reef there, like everywhere in the world, is in worse health than it was 5 years ago. And in 5 years ago, it was much worse health than it was in 10 years ago.
Yeah, really stressed the ecosystem, huh?
Yeah, about a third of the coral reefs have died in the last nominally 20 years. And so if you're in a place like that, you start to realize there's a huge issue of just assessing this. Because having gone there for many years, I could see things that other people were aware of and that they could read them, but they couldn't see them firsthand. And so I got interested in the issue of building robots that could go into the marine environment. And with a colleague at York University, Professor Michael Jenkin, we developed this proposal. We had Martin Buehler involved at the time, who's been doing legged robotics for a long time. And so we put a grant together to get a grant proposal together to do this amphibious marine kind of robotics work. Martin left as soon as around the time we got the money for other reasons. And so I inherited his lab, and I, as a result, got more into the side of building the physical robot as well as doing the software. And from there, once you're doing underwater stuff, which is in a way the hardest domain.
Yeah, combining electricity and water is never a good idea.
Right. So once you do underwater, then being on top of the water is just a small step, relatively speaking. And once you're underwater and on top, then going into the air, well, that's just one more step.
Should we get the indoor part, the early part, out of the way first?
Sure. So that probably is about 8 years worth of work. So a lot of little pieces in there, but some of it was straight computer vision, shape analysis stuff at the very beginning, hanging on from my PhD. Some of it was on the provability of localization. So for example, if you have a robot that can make a perfect measurement as to where it is, but the world itself is intrinsically ambiguous. For example, if I wake up in a hotel room and I don't know where I am, then I could be in any of the hotel rooms of the hotel. How much do I have to move around to uniquely identify where I am? So that kind of algorithmic work, what's the complexity of the path planning and path execution process of identifying your unique location? That's the kind of theoretical work that I worked on a little bit. And then we did some work on appearance-based vision for terrestrial robots, simple kind of what sometimes are called trash can robots, things that could drive around, where you might want to look at visual features in the environment and estimate where you are, which continues to be an ongoing theme in our community, although probably more in the outdoor domain than indoors these days.
And now then you got started in field robotics with underwater robotics. You really started with a hard nut to crack there.
I did, yeah. I mean, first there was a need. It's an area where there's not a lot of people working, so there's an opportunity. I was working with Martin Buehler, who had this very, very capable robot that he'd already tried putting in the water. So it looked like developing that platform, you could get into the water in a fairly natural way. And I can't deny that it's not so bad that you have to go to the beach once in a while as well.
Yeah. And I think that this is also important, that they bring the robots out there and to really, and this is probably the biggest challenge we have in robotics from now on. Only bringing it to the ocean is physically very hard with water, corrosion, very varying environmental circumstances, but also bringing robots into industrial environments, bringing them into the homes. That's clearly where we need to go, because that exposes us to so many new and interesting problems. Huh?
Absolutely, very much so. Let me mention one of the things that got me staying in field robotics instead of just going on one trip myself, that I realized when you bring a team of students to a very tough environment like that, it does something amazing, right? People join together and they become a cohesive unit very effectively. So aside from just the research agenda, as a professor, if you're training students to either work as a team or do other work or go into industry, it's an incredibly effective and valuable process. It's a little bit, like in the frosh week of American universities or in the military, they make people kind of do these weird suffering kind of games for a few days and to bond them together. And I'd never really done that as a student, but I realize inflicting that on the students in the context of this research, that alone is kind of enough to motivate me. It's a very good thing.
Yeah. Could you tell us a bit about the underwater robotics you do and how you build them and program them and what you use them for?
Sure. So we don't really work on the end user kind of applications. We more work on the developing the technology. And so we kind of do all the layers. We, historically have actually built the physical robots. We don't do the metal work. We send that out to outsource that, but we actually assemble the physical robots in the lab. We've done some design of the electronic boards over time, adopting many of the architecture and the electromechanics from existing prior platforms, of course, not inventing it from scratch, but doing some work at that level. Then we do some work on the embedded systems, some work on the operating systems kind of stuff, migrating processes between the different processors on the robot itself. And then probably the bulk of our work is on what I'll call the higher level processing, the computer vision, the navigation, path planning, collision avoidance, gate control. Lately, we've got a really cool project where the robot, which uses flippers to swim in the water, can learn brand new gates all by itself, which is a very interesting thing, surprisingly effective.
Yeah, adapting it to different currents or situation where it needs to move then, huh?
That's right. And also learning gates for specific maneuvers that no person had ever invented. So we've had a number of different roads along which we've tried to design gates, but generally there's a person deeply in the loop tuning and creating the gates. And the space of possible gates for either a legged or a swimming robot is very large. So you can, if you do it by hand, you can only explore a little bit of it. It turns out that, if you say, I want to do this kind of maneuver and let the robot learn the gate, it occasionally learns some really exciting gates that just we'd never seen before. And that's tremendously gratifying and pretty useful, I think, too.
Is this for the big blue ocean, or is it close to shore? Is it really deep?
Yeah, so our vehicle is targeted to shallow water in the oceanographic sense, meaning not more than 30 or 40 meters. And probably the primary reason is because I'm not doing the applications, I'm focusing on developing the technology. So that often means there's a graduate student or a set of graduate students in the loop, either measuring the performance, observing the system, maybe even tuning the system, or at least recovering the system if it fails completely. And so if you go much deeper than 100 feet, 30 meters, then ordinary recreational divers can't swim any deeper than that. And so there's a problem of just doing the experimental work at all. Like you can't recover the robot if it was to fail. So that's probably the main reason. The other thing is that the thing that got me in is this coral reef problem. And the bulk of shallow water coral reefs live in depths where they can get sunlight. And so as soon as you get down to kind of on the order of 100 feet, it's getting pretty dark. And so a lot of the action in the coral reef world is in those shallow water depths, although there's still very cool things at 200 feet and beyond.
I would also think that we have robots for the big blue oceans. We have the remotely operated vehicles and stuff, but there's also a shortage of robots that can act and interact closely with the environment and spend time in that very complex and very hard environment too, I would presume. Huh?
I think modeling the ocean environment at every level is pretty tricky. In the shallow water, like in the reefs, the reefs are very complicated structures and also very delicate. And also there's all sorts of current and surge. So there are particularly exciting challenges from a research point of view. And there's also a need. I think even in the deeper water, although we have these torpedo-like robots that can go for very long distances with very great endurance, that means a long time, still getting them to collaborate effectively and dynamically and autonomously instead of being pre-programmed, I think there's still a lot of work to do there. So I think I wouldn't say at all that the deep water is like a solved problem. It's the physical devices you can say, I've got those, I can buy them, I can use them. But like everywhere else, doing real intelligence or autonomy, there's still work.
Yeah, and I would also think that communication underwater is also always a huge problem. I mean, we're so used being able to use Wi-Fi and cellular communication and satellite navigation and stuff. As long as you go below the surface, all that stuff is gone, right?
Right, especially in salt water, because the ocean water is like a Faraday cage, meaning it conducts electricity. It means no radio comms, effectively no radio comms, work underwater unless you're willing to spend a lot of money at a low bandwidth. So you're either going to have no communications or only very limited visual communications, because light is also absorbed by the water, or you're going to have acoustic communications, which tends to be a little bit bulky, a little bit power hungry, and also relatively low bandwidth. So in our case, our robot really only uses visual communications as its primary modality.
Does that mean it uses light to communicate with other robots, or?
So the main robot that we did work on, the hexapod that swims underwater, only talks to other robots when it's on the surface.
Okay.
But it talks to human divers.
Okay.
And it talks to human divers using optical methods. So for example, it has a display that it can use to talk to you, and it has gesture-based fiducial language, a language of markers that you can manipulate that allow you to program the robot as well.
Cool. And this solves the communication problem for underwater use beautifully, because it's one of the major challenges. You don't work with the end application, but where do you see this being used?
The underwater domain is full of challenges. The domain I like the best is the one where you work with biologists and address some of the environmental assessment problems. Unfortunately, biologists tend not to be very well funded. So they have all sorts of needs, but they don't have the budget to sustain as many activities as we want to do as a user community, I think. Maybe that'll come, but it's not right there today. Of course, there's a lot of issues in terms of maintaining and assessing the quality of underwater resources. So resources means pipelines, boats, maybe fish populations. Fish populations isn't the ideal thing for my vehicle, but for people we work with, it is. Maybe we'll do that. You can also do that in a AUV, UAV scenario, that is a plane and a boat together, or plane underwater vehicle. So the fish stock assessment. One of the applications in our network that we're looking at doing in about 2.5 to 3 years is modeling icebergs. And if you can model the shape of the iceberg under the water, then together with knowledge of the currents and some of the weather patterns, you can predict where it's going to go. And depending on where it goes, that has a huge impact on other kinds of things that are being done. So for example, there's offshore oil platforms on the East Coast. When the iceberg heads towards them, they have to take all sorts of very expensive and somewhat dangerous precautions. Danger meaning both to the people and to the risk of spilling oil. So predicting the iceberg motion is a big issue, and so we're hoping to work on that specific application in a few years.
Yeah, very interesting. An application where a robot is probably the only thing that could do it, because these icebergs are very dangerous. They drop large parts of themselves and they turn around, and
Absolutely.
anything but a robot couldn't do that. So
it's hard to imagine, even if you were willing to sacrifice your people like crazy, which we're not. What measurement can you take without going under the iceberg with a robot vehicle?
Yeah. That's a very interesting application. The fish stock, it's a huge resource for us. It's an important resource, but it's also, to many extent, a mismanaged resource. It's been overly exploited. It's been exploited in the wrong way. Why is it challenging to do that kind of work?
Well, I think if you want to manage the resources, you want to assess what's out there. And to assess what's out there, you have to have some way of doing the appropriate sampling. And by the way, this takes place at different scales. So if we think of the cod fishery off the east coast of North America, that used to be enormous numbers of fish. And so it's like trying to assess the size of the clouds in the sky. That is, what is their boundary? They're constantly moving and changing shape. And so there's a temporal component as well. It's not a matter of just gradually swimming around and finding the boundary of a cloud, because by the time you've got a third of the way around, the whole cloud has changed shape. So that's the big scale problem, and I hope you can see it's kind of incredibly tricky.
Very challenging.
That's right. And the way we do it now, by the way, is surprisingly, I'm trying to think of a politically appropriate word, uncomplicated, let's say. But it also takes place on a small scale. So going back to this reef environment, there are all sorts of little fish that live on the reef, and their existence and their population is important. A huge fraction of the Earth's ecosystem starts out at the coral reef. So it's part of the bottom of this long food chain. And so you have to go around potentially and count smaller fish on a reef. And again, they're hiding in rocks, they're going underneath rocks. And so to assess the quality of a reef, which you're trying to save, you need to know if your efforts are working. You have to count these fish. And that also is hard. You have to count them and maybe identify them if you're really ambitious.
The species. And you said that you're also working on surface robotics. Do you do that in any?
Yeah. So we have some work with surface boats, which do navigation. I think one of the most exciting variants of that is a project where we had an air vehicle, a surface vehicle, an underwater vehicle, and some biologists in the loop as well. So a biologist at Guelph University, she's now at McGill, named Catherine Turgeon, would monitor a reef remotely using video from an air vehicle. It produced a summary of what it saw, so it automatically summarized the video. Then it would send that video back to her. She would designate areas of interest in real time. That would be transmitted to a boat on the surface. The boat would rendezvous with the underwater vehicle, and then the underwater vehicle would go to those places and take more extensive video and measurements of those locations. We actually ran that experiment. We didn't run it in such a way that we produced data that would be directly used by her, but we actually made all the pieces fit together and made it go. And so that's if things for like, or also coral reef diseases are a related problem. So you'd like to look at the reef, understand the changes in coloration and properties of the reef, and then assess whether there are diseases, which there are in general, and measure that. And so, by the way, I even trained a collaborator. My daughter, Natasha Dudek, is a PhD student, and she helped us do some of the work on measuring the diseases, which was kind of nice. Closing the loop in every way, right? Yeah. Socially, biologically, geographically.
Yeah, nice, very nice. And I think that the surface boat there probably played an important role in bridging the communication gap between the aerial robot and the surface and the subsurface robot.
Absolutely.
Because the surface robot can communicate with the subsurface robot because it can use a more powerful, maybe a diesel engine or something to give it power, and it can tell the subsurface robot, I'm here, please come to me, I have information for you. And when they're close, they can use other forms of communication.
Exactly. In that particular project, we didn't use a more powerful transponder on the boat. We've done work for a long time, actually goes back to that theoretical work I mentioned on robot rendezvous. So if you have two agents moving in some environment, both with uncertainty, what algorithms can guarantee the most rapid rendezvous? So I continue to work on that with my students. And so we use that to let the surface vehicle and the underwater vehicle find each other, create a rendezvous. Once they're close, as you say, then we can use all sorts of higher bandwidth things.
Especially for video and other work, that's of course necessary.
Right.
So where do you see this work going in the coming 5 or 10 years?
Well, before I answer the question, I'll observe, of course, that in general, the ability of scientists and engineers to predict 10 years into the future is generally terrible. And they're probably better than, say, politicians who are just as bad.
Yeah, prediction is a fool's game, especially the future, I've heard said.
Exactly. That said, I think nobody in our field would deny that robotics is on a tremendous upswing. And so we have a tremendous need in terms of land, water, terrain that has to be assessed, monitored, taken care of. And the more our environment degrades, the more it's an issue of taking care of it. Robotics provides really the only solution. I mean, it's not feasible to deploy enough people to monitor these resources and take care of them and assess them. So I think inevitably we're going to see more and more robotic systems deployed in managing our natural resources and trying to assess them. And probably to a large extent also make money out of them in many cases. If you think of mining applications or energy, not only can robots be used to look at large land masses and find out what's going on and whether things are under control, they can also help actually do the recovery of the natural resources, hopefully in a way that's more environmentally sustainable.
Yeah.
And lastly, if you have things like oil pipelines, you really want something keeping an eye on those things actively to make sure that there's no leak or bad thing going on. So I think we're just going to see robotics everywhere outdoors, not in high density, but as a major application domain.
Yeah. When we move the robot out into this very complex and demanding situation, would you see any real key part of the technology that you'd see developed? I mean, we're all talking about the batteries and power sources and stuff like that. Is there any key part here that if somebody out there has a great idea in that space, that you'd say, wow, I really want that, whatever it is?
So I think today, and probably for the last 10 years, we've seen enormous emphasis on the development of the hardware systems, including communications, sensing, mobility, all that. My gut feeling is that in the next 10 years, say, we're going to see reduced pressure on developing cool hardware because we have pretty good capacity, of course, always getting better, and much more on inter-agent communications, both between robots and people, much more on human-robot interaction. So actually having robots that are controllable, especially if you think of a scenario where one person is controlling a team of robots, doing that in a way where the person's not essentially just teleoperating an impossible number of robots to the point that they're either going out of their mind or doing a bad job, that's going to become an issue. And I think also being able to build long-term models by these systems themselves, for example, on when their plan is failing and they have to do a completely new thing. So, large-scale replanning, I think,
machine learning in one way, where they can learn and adapt to the situation.
Well, it might be machine learning. It might also be other kinds of planning. Let me give you an example of a problem like this, if I could. So one of the things that we've started to work on is, since we have an amphibious robot, this robot that we have swims underwater, it can also walk on land with an appropriate set of amphibious legs. And so we wanted to be able to walk along the beach, go through the waves in the ocean, which might be substantial, and out into the water. And so we can do that under teleoperation if the waves are not too big. But if you look at what, surfers or turtles or almost any agent that does this task has to do, first of all, they have to measure whether conditions are right. Then they have to try to do it. And with non-trivial frequency, they fail. They get flipped upside down or sideways, and they have to come back out of the water and try a second time. And so if you think of this is a microcosm of a bigger problem, but what a robot would have to do, almost inevitably, it'll have to face that because turtles have had a time to work on it a lot over the last 65 million years, and they're still worrying about this. So you need a robot that can try to get in the water, realize that its attempt is failing, and it has to back off and retry. And so that process, we could call it AI, we could call it machine learning, we could call it some sort of multi-level planning. I think all those words might be the appropriate technology, and maybe all of them combined.
But I think that this space where we're really, really close to shore, I think that space being not only going from shore to the deep blue ocean, but actually staying in this border area, because a very, very large part of human interaction, both positive ones where we harvest the resources or we enjoy the space or we pollute it, is happening in that area. And that's something I understand is under-addressed by current systems. So spending time in that, you save waves, you see very close to the ground or the bottom of the ocean. Very interesting space to operate in.
Absolutely, right.
But also very challenging.
And it's a great place as a researcher to work on because it's so challenging, right? It's not so hard that we can't make progress, but it's hard enough that there's lots of interesting things to do. And also it's very nice to work on a problem domain where you feel that if you have success, this will have a positive impact on the world, right? It's actually doing something very good, very green in a way.
It's a deeper meaning to what we do, right?
Yeah, absolutely.
Yeah, perfect. Thank you very much for taking the time to do an interview.
It's been a pleasure to be here, and I hope to see you again.
I hope you enjoyed this episode of Robots in Depth. Please subscribe, share, and visit us on robotsinDepth.com. You can also support us on Patreon. Robots in Depth is supported by Optomica and Robots Up Close. Optomica, rent anything in modular robotics and build whatever you can imagine. Robots Up Close, travel the world and see what's going on in robotics right now, up close and personal. I would also like to especially thank the organizers of the Robo Business Conference for their gracious assistance, without which this interview would not have been possible. I am Sjöborg, and I thank you for watching.